Okay, today we're working out of 12.4. It's the last section from chapter 12 we're going to look at. And in chapter 12.4, we're going to start by looking at what's called the partial sums. Now in 12.3, we were doing essentially a partial sum of a geometric series. But here we don't have the summation notation. This is what we're used to seeing. We're not going to use that in this first part of the assignment. We will later, but early on, all we're going to do is list all of the totals and see if maybe it's going to approach a certain value or if this is going to get infinitely large. So what we're going to do is we'll maybe put these as decimals. And 2/3 is 0.67 or so. Again, that's a rounding. But I'm going to take 2/3 plus 1/3. 2/3 plus 1/3 is 1. 3/3 or 1. And then the next one is 2/3 plus 1/3 plus 1/6, which turns out to be 1.17 essentially. And then to find the next term, I take 2/3 plus 1/3 plus 1/6 plus 1/12 to get 1.25. And then I do it again, to get 1.29 essentially. And there's probably a little bit of rounding there along the ways. But I just want to make sure that I'm very thorough, that I don't round what I put into the calculator. What's coming from the calculator and I write down is okay to round. But I wouldn't want to round and then put that number back into the calculator. For instance, I wouldn't use 0.67 and add a third because it wouldn't produce 1. I would use 2/3 to add to 1/3, and that gives me my 1. 0.67 is not really what you want to put in the calculator. But the point that we want to look at is if you look at how much change there is here, this is a 0.33 change. So let me first off say this is my answer. Okay, this is a 0.33 change. This is a 0.17 change. This is a 0.08 change. This is a 0.04 change. The change is very small, very subtle, and it's probably going to change a couple more times. But I might start to flatten out. Oh, probably around 1.5. We're looking at somewhere around there that we're going to be minimum or maxing out at, somewhere around that ballpark. Maybe a little bit bigger, maybe a little bit less, maybe 1.33, somewhere around there. We're starting to flatten out, and then we just want to see that there's a pattern. This is not growing at the same rate. It's slowing down, and that's part of what happens with these geometric series. Sometimes they do slow down. Then we're going to look at number 13. There is a formula for a geometric series when we're adding it to infinity. When we're going from 1 to infinity, or from a number to infinity, this is an infinite geometric series. And the formula is that it will equal a sub 1 over 1 minus r. Well, a sub 1 always comes from taking the first value and plugging it in. 1 minus 1 is 0. 0 and a negative 8 over 9 to the 0 power is 1. And 1 times 7 is 7. So this is 7 over 1 minus, and my r value is negative 8 over 9. So I end up with 7 over, when I add them, okay, when I add these down here, I have 7 over, this is 9/9 plus 8/9 is 17/9, which when I reciprocate makes 63 over 17. And there's my answer for this series. Okay, there's a decimal approximate for that. That is 3.70588. And I'll take either one of those. It's fine. I like the fraction a little bit better, but I understand why you might come to that value. Now this works really great so long as r is less than 1. Now the absolute value of negative 8 over 9 is 8 over 9, which is approximately 0.8 repeating, which is less than 1. Because this r value is less than 1, this formula right here is perfect for taking an infinite series. Let's go and look at number 22. 22 doesn't give me that summation notation, but I can build it if I need to. The first thing I want to know though is what's my R value? The way we found R for all geometric sequences or series is we take a specific term and we divide it by the term before it. So divided by 4/15. So 4 over 9 divided by 4 over 15. And this is a reciprocate multiply, or you can put it in the calculator. 4 over 9 times 15 over 4. The 4's cancel, and the 9 and the 15 both divide by 3, leaving me with 5 over 3. Now notice that this is 1.6 repeating, which is greater than 1. So my R value is actually too big. Anytime your R value is greater than 1, and you're talking about going to infinity, notice the dot, 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 it's going to go forever. That means that this has no sum. Another way to say that is that this is going to add up to infinity. It's going to keep adding and get bigger and bigger and bigger. Never stop. See, this other one, it was going to force us to stop right at this number. This is where we're going to get to as we added those numbers. All right, last one, number 31. In class we talked about how a repeating piece can be written as a number over 9 or over 99 or 999, as many 9s as it takes to create the repetition. So what I really want to do is I want to write this in repeating form. So 0.27 repeating, the 7's repeating. And so because the 2 is not part of the repetition, I'm going to have 0.2 plus 0.07 repeating. Okay. Now, the 0.2 is 1/5. The 0.07 repeating is only the 7 that repeats, so I'm going to put 7 over 9. That's going to give me the 7 over and over and over again. Unfortunately, when you check the calculator, this gives you 0.7 repeating. Okay, so I need to figure out a way to move the decimal left and fill it in, so they get that O in front. To do that, I'm going to divide by 10, which is the same as to multiply by 1 over 10. So this is 1/5 plus 7 over 90. In order to add these two fractions, I need a common denominator. So that's going to make this 18 over 90. When you multiply top and bottom by 18. And that gives me 25 over 90, which reduces to 5 over 18. Now to prove that that works, you take your calculator, you type 5 divided by 18, and sure enough, this is what you get. So our answer checked out. Most of the problems in the section that 31 comes from are actually a little bit easier. This is just to help you with, that 1 or 2 problems where you might have really had some problems. So good luck, and we'll see you in class.